Great, thank you. All right. Um, can is this all fully audible? Okay, great. Um, all right. So today I'm going to talk about robotic learning with large data sets, general purpose models for all robots. To start us off, let's discuss a little bit of perspective about how AI used to work and how it works today. So it used to be that if we wanted to solve a particular AI problem, like for example, image segmentation or image classification, we would collect a separate labeled data set for each task, typically a pretty large data set, get human labels for it, and then train a separate model. And we would do this for all sorts of applications, for classification, image captioning, NLP, sentiment analysis, summarization. Each of these would be a separate model and a separate data set. And these days, the way that we tend to think about AI systems is that we have a very large and relatively lower quality data set, maybe just data mined from the web, that is used to pre-train a very large unsupervised or self-supervised model, sometimes called a foundation model. And then these models are then fine-tuned to downstream tasks or even just prompted in few shot to solve a downstream task. And this is the case for language models. It's the case for contrastive vision language models, for all sorts of other contrastive learning methods in computer vision and so forth. So let's try to map this idea onto robotics. Robotic learning today generally is kind of in that same place as AI systems used to be, where if you have a particular task you want the robot to do, like flipping a pancake or something else, you would train a separate model for each application domain with data collected for that robot, whether it's imitation learning or reinforcement learning, and it would really be specific to that setting, that robot, that task, and so on. So perhaps in the future, if we want to tackle robotic learning challenges, we'll have a large data set of all sorts of different robotic behaviors, which we'll use to train a giant unsupervised or self-supervised pre-trained robot model, the kind of robot foundation model, which would then be fine-tuned to particular downstream robotic tasks. And I think if we get there, this will put us in a much better place with robotic learning because we'll be able to leverage the benefits of huge data sets and huge models without requiring huge data sets to be collected for every single robotic application. And this will actually make it much more practical to bring the full power of machine learning to bear on the robotics challenges. Okay, so how can we get these kind of generalist robotic foundation models? And if we want to try to think about that, maybe we can start again with mapping this back to standard AI techniques and ask, how did we get generalist models in other areas? Well, we can think of it as a progression where you can start with small, very task-specific data sets, then through a lot of brute force labeling, progress to larger domain-specific data sets, maybe like, ImageNet versus MNIST, and then eventually get to very large and kind of domain agnostic data sets of the sort that are most widely used in NLP, like Common Crawl and so on. And you can think of these different data types as being on a spectrum where the further you go to the right, the bigger the data sets become, but also the models become more general. The reason they become more general is because there's only a limited amount of data for each application. So if you want a huge amount of data, it'll have to be across applications, which means that the models will have to be more general. And that's both a good thing and a bad thing. It's a bad thing because it's, of course, harder to build a general model. But perhaps the other subtle but very important point is that the data becomes worse. The labels become weaker. If you want huge amounts of data, you probably can't rely on that data being extremely specific to your desired target domain, nor can you rely on that data having extremely good labels. And that means that your learning methods have to make fewer assumptions. So to get generalist models, the biggest enabling factor is the ability to use more data. And therefore, if you want to map this onto robotics, the question is how you design robotic learning methods that can use more and more data without necessarily making those strong assumptions and being able to leverage weaker data sources. So what kinds of data can we use for robotic learning? Well, we have high quality data, which would typically be single task and single robot, and also strongly labeled either with optimal actions for imitation learning or optimal task rewards for reinforcement learning. Then you can progress further to the right and have multitask data, perhaps less optimal demonstration data, or even fully suboptimal autonomous trials. Further to the right, you can have multi-robot data that is not specific to either the task nor the robot type. And then even further to the right, you could even include video data, which is not even specific to robots, but still depicts activities and behaviors that you might want robots to perform. So As our learning methods improve, the more they can move to the right on the spectrum, the more data they'll be able to consume, and the closer we'll get to being able to build robotic foundation models. So what I'll talk about in today's talk is some of the things developed in my group over the last year or two that I think move us further to the right on the spectrum. I would emphasize that there is a lot of work yet to be done, but hopefully this will give you a sense for what kinds of ideas could move us further to the right and therefore closer to the robotic foundation model. So I'm going to talk about first goal condition policies, which relax some of the requirements for strong demonstration data. I'll talk about offline RL with rapid fine tuning. Then I'll talk about learning from videos and action-free data. And lastly, I'll discuss some work on cross-embodiment robotic foundation models that can use data from many different robotic sources. So let's start with a discussion of goal condition policies. If we want to start working on large-scale robotic learning and robotic foundation models, of course, we need to start with some kind of data set. And one of the things that we've been doing in my lab at UC Berkeley over the last couple of years is taking this idea very seriously. So we collected a very large data set called Bridge Data V2, which is intended to support this type of research. Bridge Data V2 has over 60,000 trajectories and interactions with hundreds of objects. All the trajectories do have full language annotations, and there are 24 different environments. And that's really important because if you want to train policies on this data set that will generalize across environments and run in other people's labs in order for the data set to actually be like reusable by different researchers, then you need many environments to be present in the training set. And we've in fact confirmed that policies trained on the bridge data can be evaluated and used successfully by other labs other than our own, which is really, really important to really support this kind of research. The robot used in this data set is a low-cost Widow X arm, which is relatively inexpensive to obtain, and that's also important for making this kind of research accessible. But what I want to tell you about today is how data sets like this can be used to produce fairly general policies with comparatively few assumptions. So here's a very simple idea for how to train a generalist policy if you have a data set like this. We're going to do goal-conditioned learning, where our policy takes in the current observation, shown here at the top, and a goal observation, an image of what the user wants the world to look like. And you can produce this goal observation just by moving objects on the table yourself, taking a picture, and then essentially asking the robot to figure out how to reach that state. So the current image goes in, the goal image goes in, and the robot action come out. Very simple. Now, it turns out that there's a very simple training procedure that can allow you to train these kinds of policies. It's not a novel procedure, it's been known for quite some time, but it turns out that if you take this procedure and you use a good enough data set, really good things can happen. So the procedure works like this. You take your data set and you pull out a trajectory. And along that trajectory, you sample two time steps, an earlier one and a later one in green and orange. And then you construct a training tuple where the inputs are the green and orange image, and the output is the action taken at the green image. So that's your training tuple. The reason this works is because you know that whatever action was taken at the earlier time step, the one shown in green, eventually led to the later time step shown in orange. That doesn't mean it's the optimal action to reach it, but it means that it is an action that in principle could eventually reach that orange state. Now, if you want to make this precise, there's all sorts of technical assumptions that go into this, but broadly speaking, this actually works. It's a very, very simple procedure because the subroutine for training after this is regular supervised learning. But crucially, it does not make the assumption that the data is either optimal nor annotated with language annotations or anything like that. Interestingly, the bridge dataset does have language annotations, but this procedure does not require that assumption, which means that in principle, it can use broader and more diverse sources of data. And here are some videos of this goal condition behavior cloning policy trained on Bridge V2. Now, again, the training procedure here is not a novel contribution of this work. It's been known for years. What is new is the particular data set. And you can see that the policy trained on this data set with goal condition BC can actually perform a pretty broad range of tasks. This is the same exact policy performing all of these tasks. And you can see that it can sweep up dirt, it can fold cloth, it can open drawers, all with one single neural network, just by basically having the right data set. Now, of course, goal condition policies are probably not the thing that we actually want in the end for robotics. We'd like humans to be able to communicate with robots in intuitive ways, for example, by using natural language. So what we would really like to do is retain the generality of this approach, the ability to use all sorts of unlabeled trajectories, but somehow retrofit the ability to follow language instructions. And we've explored a number of ways of doing this. One way of doing it is to use large amounts of data without language annotations, and then a small amount of data that does have language annotations, and somehow combine those two sources. So this was done in a paper led by Vivek Myers called Goal Representations for Instruction Following, where the idea was to build an aligned space that contains both goals and language instructions so that you could have a small amount of data with language instructions and a large amount of data without it that is used for goal conditioned behavior cloning. So essentially the goal representation supports both images and text. This is conceptually very similar to CLIP, for those of you that are familiar with it. The main difference being that now instead of embedding images and text into the same space, it embeds pairs of current state and goal state, basically a change in state, into the same space as a textual instruction. There's quite a bit of additional machinery needed to make this actually work in order to have the policies support this cross-modality goal representation. But broadly speaking, the procedure ends up being very similar to goal condition BC, just with a representation that aligns text and images. And if you can do this, then you can train on the same bridge data set using only a small fraction of the textual annotations and then carry out a wide range of language commands significantly more effectively than alternative methods. So these results, the orange bar shows a success rate of this method called GRIF. The blue bar shows what you can think of as a goal condition BC method without the alignment technique. And BCZ, the gray bar, is a more traditional behavior cloning approach that performs imitation learning on the language label data. And you can see that in 2 out of these 3 scenes, there's a very large improvement, more than 2x, from using this alignment technique. Again, this is one of the ways that we can use lower quality data because we do not require the assumption that all of the data has those language annotations, and we can use data that is unannotated and perhaps lower quality. It turns out, though, that we can actually incorporate language instructions potentially without having any annotations at all, or leveraging internet scale data with annotated images without necessarily requiring those annotations to be on the robot data. So the way to do this is to actually leverage recent advances in image generation models such as diffusion models. So what we can do when given a command, like put the orange crayon in the wooden bowl, is instead of training a policy that can interpret that command, we can train an image generation model that can look at the current image that the robot is seeing and the instruction, and then actually synthesize a new image that depicts what the scene would look like if the robot were to execute that instruction. So the synthesized image for put the orange crayon in the wooden bowl might show the gripper over the orange crayon. And now if we can build this kind of generative model, then the robot only needs to know how to follow image goals. So we can use that really simple goal condition BC technique from before, and now it would actually be able to follow language instructions because the diffusion model would turn those language instructions into images. Now, one of the nice things about using an image diffusion model as the way to interpret these instructions is that it's now very, very easy to incorporate non-robotic data into the training process. So here you can see 2 sets of goal images. Each one is produced for the same command. So the top one is fold the cloth from bottom right to the top left corner. On the right, you can see the image generation result from a model that is fine-tuned on both the bridge dataset and the something something video dataset. Now, the video dataset depicts humans rather than robots, but the image generation model still only operates on images, so it's very easy for it to use video data from the web to assist in this fine-tuning process. Here are some results. So this is the synthesized image for a goal, for a sub-goal for the instruction shown at the bottom. And then after each synthesized sub-goal, you can see the robot actually performing that sub-goal. So you can see that the model doesn't just generate the final image for the task actually being completed, it actually guides the model along with the individual sub-steps. So here's the final sub-goal, and the robot performs the task. So the diffusion model guides the robot along through each step of the task, and the diffusion model benefits from lower quality data, such as video data, that is sourced from the web. And again, this is important because this shows that we can use data from more sources. In this case, we can use data from the internet that is not robotic data to assist in training the sub-goal predictor, and then use the goal condition BC model trained on the bridge data to actually execute those sub-goals. Okay, so that's goal condition policies. But now let's talk about moving even further to the right on the spectrum and being able to use even lower quality robotic data. So one of the ways that we can use suboptimal data is to leverage offline RL instead of imitation learning. What do we expect offline RL methods to do? Well, some simple intuition, which is maybe a little bit misleading, but pretty common, is that offline RL is like imitation learning, that maybe in offline RL, you have trajectories that perform a task, and it allows you to imitate those trajectories better. but that intuition is maybe a little bit inaccurate. A more accurate picture is that offline RL is kind of about getting order out of chaos. So if you have a variety of trajectories that go in all sorts of different places, maybe many of them are completely suboptimal, if you just take the bits and pieces of the individual behaviors and recombine them in a new way, then you can perform a task much more optimally than any of the individual examples that you saw, essentially using the examples to figure out what is possible, and then from knowing what is possible, figure out what would be optimal for your task. And of course, there's a simple version of this that happens kind of at a macro scale, where if you've seen an example that goes from A to B, and you've seen an example that goes from B to C, you should be able to figure out that it's possible to get from A to C. But the real promise of offline RL is that this kind of happens everywhere all at once. So if you see lots of suboptimal trajectories, if you recombine the best parts of them, you could do better. Imagine that you have data of driving from lots of human drivers. If all of the human drivers are suboptimal in different ways, if you combine a new policy that is as good as the best driver in each situation, you will overall be significantly better than all human drivers. Most current offline RL methods are based on Q function estimation. I won't talk in detail about how these methods work. What I want to really focus on are the robotic learning results that demonstrate how offline RL techniques can enable utilizing broader sources of data and therefore get us closer to robotic foundation models. But if you want to learn more about the methods, I would encourage you to check out these two papers: Conservative Q Learning for Offline Representation, for Offline Reinforcement Learning, and Offline Reinforcement Learning with Implicit Q Learning. These two papers describe some fairly widely used techniques. There are also much more recent methods, but these could serve as a decent starting point. Okay, so let me tell you about a robotic learning result that utilizes offline RL in a way that I think illustrates our ability to leverage broader data sources. So this was a result that was actually led by some researchers at Google, Yevgen Chebutar and Quan Wong, called Q Transformer. And the idea was the following. We had a system called RT1 that we developed at Google some time ago. And RT1 was an imitation learning system. It would imitate language instructions, and it could do some pretty exciting things. Like it, for example, could navigate to a drawer, open the drawer, take out some chips and bring them to the table. But it required high quality demonstration data. And at Google, we could collect this high quality demonstration data, and it was okay, but the data was expensive, and we needed a lot of manual effort to collect and curate that data. So we thought, well, what if we take these 38,000 demonstrations with language labels and add in unsuccessful attempts from the robot itself trying to perform these tasks? Now, in reality, when the robot attempts these tasks, sometimes it succeeds and sometimes it fails. But to make a really controlled experiment, we actually only kept the failed trials. So we just threw out all of the additional successful trials just to keep the comparison fair. So we really wanted to answer the question, does adding failed trials from the robot itself improve the policy over just imitation learning? And what we developed is an offline RL method that was suitable for training RT1 style models. RT1 is a transformer-based policy that uses tokenized actions. So we needed an offline RL method that could train transformer-based policies with tokenized actions. So this was essentially an offline RL trained RT1 model. Here's the idea. The model is a large transformer that reads in images and reads in textual instructions, and then it outputs per dimension tokenization of the actions. So for every dimension of the action space is discretized, turned into a token, and the model outputs that token. So to make this work with offline RL, which requires Q function estimation, what we actually did is we had each dimension of the action correspond to a different time step of an underlying discrete action MDP. So instead of treating robotic control as a continuous action MDP with every real world time step being an MDP time step, instead we had more time steps where every dimension is a time step, but now the actions could be discrete, which means the same tokenization could be used. So it's a discrete action algorithm with more time steps than the original problem multiplied by the dimensionality of the action. It actually does these Bellman backups across dimensions and then uses a method similar to contrastive RL, to conservative Q learning, to CQL. So here are some videos of Q Transformer performing a variety of language conditioned tasks. So the same policy was trained across many different tasks, dozens of tasks, in fact, and it could perform a wide variety of instructions. But the important results are the quantitative results. And here we're comparing Q Transformer QT, the first column, to a variety of different methods: the Decision Transformer, IQL, and the rightmost method is RT1, the original imitation learning technique, which does not use those failed episodes. this is showing three categories of tasks. Within each category, there's a very large number of tasks. So the total number of tasks in our evaluation was on the order of about 70-ish. And you can see that there's more than a 2x improvement in the average success rate of Q-transformer over RT1, which means including those failed trials actually more than doubled the success rate, which I think is pretty remarkable because the number of failed trials is not that, it's actually smaller than the number of successful trials, and of course they're all failures. So this really shows that once we switch to offline RL, we can really leverage much broader sources of data in the sense that we can use autonomously collected failed attempts. Now, what if we want to use offline RL to actually adapt to a new task rather than just doing better at the existing tasks? One of the things we could do is pre-training with offline RL. So in another paper called Pre-Training for Robots, led by Aviral Kumar and collaborators, we took an earlier version of the bridge data set and we trained a model with offline RL, in this case, not conditional language, but conditional task ID, that could perform all the tasks in the bridge data set. And then we experimented with whether we could take a new task and then fine-tune with offline RL to that new task. Now, it takes a little bit of detail to make this work. The fine-tuning procedure actually recycles batches from the pre-training data set because the fine-tuning data is so small. Here, fine-tuning data was just 10 trials for the target task. But basically, the concept behind this project is to use offline RL for fine-tuning, very similar to how pre-training and fine-tuning is done with supervised techniques. And what we saw is that actually we could do this successfully. We could fine-tune to a new task that's structurally similar to tasks seen in the bridge data set, but different in some way. In this case, the task has a different environment and a different object. So the robot has seen tasks that involve putting objects into a pot, but other objects in other pots, and now it has to put a cucumber into a red pot in a new kitchen environment. We compared this technique, which we call PTR, to a variety of other pre-training and fine-tuning methods in the robotics literature. Perhaps the most interesting comparisons are the ones shown on the right. R3M and MAE are computer vision-inspired pre-training methods adapted to robotics that learn visual representations from the pre-training data and then adapt using those representations to the downstream task, in this case, the 10 trials for the target task. And you can see that PTR, our method shown on the far left, achieves a much higher success rate than these representation learning methods, which suggests that actually pre-training with offline RL to perform these tasks is much more effective than merely learning visual representations. And the other thing that we see with this approach is that as the network gets bigger, the performance of the downstream task improves. So the x-axis here is the size of the model, ranging from a small ConvNet, the Impala model, to ResNet 18, ResNet 34, and ResNet 50. And as the models get bigger and bigger, the performance of the downstream tasks improves, which means that we're actually benefiting from scale in the way that we would expect from large-scale machine learning techniques. Now, how about online RL fine-tuning? So far, the results I showed fine-tuned from 10 trials that are provided by a human, so it's offline RL fine-tuning after offline RL pre-training, but we can also do offline RL pre-training and do online RL fine-tuning, actually run regular autonomous trials and see if we can improve through iterative attempts. So here, the robot is fine-tuning to open a microwave door. Initially, it has a reasonable idea, but it's not successful. Then we run more online RL with a variant of CQL called CalQL, and the robot gets a little bit better. And then eventually it actually succeeds at the task and is able to open the microwave door. And here all it's getting is supervision from a sparse binary reward indicating whether the door has been opened. So the performance improves from 53% to 73% on all of the positions of the door. And if we just test the novel previously unseen positions, 13% to 60%. So offline RL can enable acquisition of new skills with 10 to 20 demos, and then using cheap autonomous data can actually make that even better. Okay, now let's move even further to the right on that spectrum. Let's talk about how we can use not only suboptimal data or autonomous data for downstream tasks. Let's talk about how we can better use data without any robots at all. And I already alluded to this a little bit when I discussed the diffusion project from before, but in fact, we can actually incorporate video data directly into the RL process itself with a novel technique based on a particular kind of Bellman backup. So before we get into the technical aspect of this, maybe a high-level question we should ask is, how should we think of video data in the context of robotics? Well, we have robotic data. Robotic data sets have to come from robots, and they might be a lot bigger than you think, like with things like bridge data and recent innovations like Droid, which is a new data set led by Chelsea Finn's lab. There are actually fairly large robotic data sets in existence right now, but they're still limited in size. So if we go to the internet and we get a huge data set of videos from the web, it'll probably always be better than the kind of robotic data sets that we can construct today. Video data can be mined from the web, recorded from humans, and so on. But then the question is, what does it teach us? Because clearly we can't get robotic actions from there because it doesn't even depict robots. So here's how we can think about video data. Let's say that you have a trajectory of a video, and you have two states along that trajectory, two images basically, a green one and an orange one. Well, one of the things you know is that orange comes after green. Like whatever happened in that video, the outcome seen in the orange image is possible to achieve starting from the green image, assuming that there's not too much stochasticity. Now, that's not very useful because what you want to learn is how to do control, not just what comes after what. But let's say that you have another video where one of the frames is similar, the blue frame is similar to the green frame, but then the video goes into a different place and reaches a different state shown in yellow. So now, because blue and green are similar, you should be able to infer that green can lead to either orange or yellow, because you have two states that are similar, blue and green, and they led to two different outcomes, which means that probably both outcomes are possible from the same state, provided that you have the right measure of similarity. And now this is a very useful piece of knowledge, because now you can actually use this piece of knowledge to learn about making decisions, because it suggests a certain branching structure that this nexus in green or blue leads to two possible outcomes, which means that if you prefer the yellow outcome and you find yourself in the green state, the yellow outcome is probably possible. So more precisely, if you're at green, you can reach yellow if you try to reach yellow, insofar as the world is under your control, which is an assumption that you make. So the key idea is to use videos to learn which outcomes can result from which states, what is possible from each situation. And this turns out to be a great way to initialize value functions, because value functions in reinforcement learning predict essentially how likely certain outcomes are to happen. And the particular kind of value function that we can train is something called an intention condition value function, or ICVF, which is a value function that is conditioned on a state, an outcome, and an intention. An intention is a state that you're trying to reach. An outcome is a state that you actually reached. And this value function is a type of generalized value function, basically predicts the likelihood that you will achieve a particular outcome if you are attempting to reach that outcome or some other outcome. So it's basically directly quantifying this question. At green, I will reach yellow if I try to reach yellow, and it outputs essentially probabilities. These intention conditioned value functions, under some admittedly very strong assumptions, are provably sufficient for representing all possible tasks. So if you can train ICVFs exhaustively with infinite representational power and infinite data, they will learn all possible tasks. Of course, with a finite sample of videos, they won't learn all possible tasks, but they will still serve as very good initializations for downstream RL. So that leads us to the following procedure, which we call VPTR, or video pre-training for robots. First, in phase one, use this ICVF technique to train a generalized value function on human videos. And this generalized value function will serve as an initialization. It will serve as pre-training for phase two, where we will run the PTR procedure from before on a smaller amount of robotic data. And imagine that you might have 4 million videos and, 70,000 videos, 4 million frames for the natural videos, and then you might have 150,000 frames or 3,000 trials for the robot data. So more than an order of magnitude step down in the size of data. And then in phase three, you can fine tune this to the particular task you want, some fairly difficult task like sweeping up dirt, using just 10 trials and a few hundred steps. So each step serves as the pre-training for the previous one. So this is VPTR. I could, of course, go into a lot more detail, but I don't want to run out of time here. So if you want to find out more, check out this paper called Robotic Offline RL from Internet Videos via Value Function Pre-Training. In terms of the results, a VPTR actually works pretty well. Now, these are fairly difficult tasks. Again, they still have lots of room for improvement. These tasks have more distractors in them than the tasks I showed before in the original PTR evaluation. But one of the interesting things I want to draw your attention to are the two rightmost columns. The second from the right shows regular PTR, which doesn't include the video data. The rightmost one actually omits phase two, so it has videos and the downstream task, but doesn't have the large-scale robot data. And you can see that omitting the video data is, in this case, like pretty much just as harmful as omitting the robot data, which means that both sources of data are actually having a big benefit. And that really illustrates that this is truly moving us further to the right on the spectrum, where we are fruitfully making use of both larger multitask robot data sets and non-robotic video data sets. And we can do this for language condition policies too, and that also leads to significant improvement over regular PTR. Okay, so now we've moved a little further to the right. In the last section, I want to talk about how we can get even closer to true robotic foundation models by leveraging data from many different kinds of robots. So the first thing I want to tell you about is some of our efforts on building a robotic foundation model for navigation. This work is actually a little bit older at this point. It's about a year and a half old. And it started with a project called GNM that was led by Dhruv Shah and Ajay Sridhar. The idea was to take data from a variety of different ground robots and try to train one model that could control all of these robots together and see if that leads to significant benefits. So what we did is we collected both our own data sets and also data sets that others had posted on the web. Turns out that these data sets came from 6 different types of robots, ranging in size from small-scale RC cars to full-scale ATVs. About 60 hours of data in total. And then we used that data to train a goal condition BC policy, very similar to the one that I presented before at the very beginning when I talked about bridge data, with the main difference that this goal condition BC policy now took a context window, essentially showing the history of recent observations from the robot. And that context window is important because it allows the model to determine what type of robot it's actually controlling. It turns out that this model could not only control the robots seen in the training data, it could also actually generalize in zero shot to entirely new robotic types. What you're seeing in the top left here, for example, is a video of a drone flying through hallways. There was no drone data in the training set. The training set consisted entirely of ground robots. Now, I will say this drone is pretending to be a vehicle because the drone is flying at a fixed altitude, so the control is still like a car, it's directional. But it is a different robot, it has a different camera. Obviously, its dynamics are different, but the model can actually generalize and successfully control the drone and avoid obstacles flying through hallways. Here is a kind of a montage of all sorts of different systems in all sorts of different environments that are all controlled by the same exact neural network. One of the things that this model can do is it can actually generalize effectively to changes to the robot. So we could, for example, introduce some damage where, in this case, a stick is placed into the wheel, which changes the robot dynamics. After that damage, a naive model will actually not steer the robot correctly, but the GNM model, because it's seen many different robot types, it can actually generalize to the damaged robot as though it was just a different type of robot and navigate it successfully to a destination. And here's again that video of the drone. So here you can see the current observation in the bottom left, the gold image in the bottom right, and it's successfully flying the drone through a hallway. We more recently extended GNM to use a large-scale transformer-based model to further improve its generalization capability and its ability to utilize large data sets. So we call this the visual navigation transformer. And this is now an open source model. You can download it at this URL. A number of people around the world have actually used the visual navigation transformer VINT for a variety of downstream applications. Here are a few different robot types that are controlled by VINT, legged robots, indoor robots navigating different destinations. You can do prompt tuning with VINT, so you can actually replace the goal encoder with a different type of encoder for some other kind of instruction, like, for example, turn-by-turn instructions out of Google Maps. And you can do things like adapt VINT to actually do driving in Carla. I apologize, the video is not playing, but this is in the Carla simulator, adapted from a small number of trajectories. I can follow turn instructions like turning left and turning right. We can also do RL fine-tuning from this kind of multi-robot pre-training. So in this project called FasterLab, what we did is we performed, in this case, actually offline RL rather than goal condition BC pre-training, but very similar to the GNM project, from a multi-robot data set. And then we perform online RL fine-tuning from that initialization. And the online RL fine-tuning process actually ends up working quite a bit better. I apologize, let me restart this so the video plays. There we go. So the online RL fine-tuning works quite a bit better than it does from scratch. With online RL fine-tuning, after just 15 minutes directly from raw pixels, in this case, the robot is trying to race around this indoor track, it can actually more or less navigate, albeit slowly, and after 25 minutes, it can actually race around this indoor course going around the hallway at more or less the same speed as an expert human, in this case, the graduate student that was doing this project, if they use the same first-person camera. So here's the first-person result. This is just 25 minutes of online RL training. 25 minutes of online RL from raw pixels typically wouldn't yield a useful policy, but because of this offline RL pre-trained model that uses the multi-robot data, it can actually do this successfully. And the multi-robot data used for pre-training doesn't actually include any data from this robot. Here is a similar result outdoors. So this is the initial policy before the online RL phase, and you can see it's doing something, but it's not doing too well. But then after, again, this is about 30 minutes of online RL training, it can actually race around this course successfully and will exhibit some interesting behaviors where in between the checkpoints, so the checkpoints are on the grass, it'll actually prefer to drive a little bit on the paved paths so that it can go a little faster. So there it goes on the paved path and can go quicker on the paved path. And here's the first person view where you can see just how shaky the camera is. So this really is a fairly difficult task because of the amount of camera shaking and the complicated dynamics of driving on bumpy ground. One question that we were really interested in with Vint is the degree to which these multi-robot policies are actually deployable in other domains. And it turns out that it actually does work around the world. And every few months we get some emails from folks that have used Vint or later models like Nomad in their own settings. So this is a result from a university in Estonia that used a variant of the Vint model for an orienteering task where they had a ground robot driving outdoors through the Estonian countryside for hours and hours trying to find particular locations. Here is a result from Finland showing a ground robot navigating their university campus, and their research was on, as I understand, on topics related to semantic navigation. And they essentially used Vint as a plug-in low-level controller just to perform the low-level control task, so they could study their interesting high-level semantic navigation problem. Here is a result from Princeton. This was a comparison. So the authors were developing their own controller for these drones, and they compared it directly to our controller without any modification, just directly using our weights, without training it on their system. We can demonstrate these robots in real-world settings. So we took it to a conference and had the robot drive around, avoiding humans. Interestingly, the model was not actually trained in the presence of humans. It was trained in a lot of forests. So I think it probably thinks the humans are trees, similar kind of profile, and the obstacle avoidance works. Now that's for navigation. Of course, we could ask the same question about cross-embodiment training for robotic manipulation. And recently, we studied this question in the context of the RTX project. This was a very large project, a cross-institutional collaboration, but it was led primarily by Quan Vong and Carl Perch. The idea in RTX was to take a variety of data sets, including the bridge data from before, but also many other data sets from 34 different labs, and combine them into one giant cross-embodiment data set with 22 different kinds of robotic arms, 527 skills, and 60 different data sets in total. Now, all of the arms were, end effector controlled 6 or 7 degree freedom arms with parallel jaw grippers. So the hardware is not that heterogeneous, but there is a lot of variability. And just to emphasize the variability, here are videos of the different kinds of situations depicted in this data. So you can see very different camera views, very different objects, very different tasks. The statistics for this are in the data set, and there's a really nice visualizer that my student Debo Ghosh built that you can access at this URL. It is a very heterogeneous data set for robotic manipulation, probably the most heterogeneous one in existence. It has about 1 million trajectories in total. Now, one of the things we were very curious about is whether a single policy trained on this entire data set could actually improve over individual specialized policies in each domain. Because something that we've seen in other areas like NLP, for instance, is that specialized solutions, like I mentioned at the very beginning of the talk, for things like text summarization or sentiment analysis, are outperformed by modern foundation models that are truly generalist models. So if we train a generalist model on the RTX dataset, does it outperform the individual specialists in each domain? And here are some of the tasks that we were testing. These tests were conducted, again, by a number of different universities around the world, from Freiburg to New York to UC Berkeley. And on average, across the different institutions that tested these policies, they found that the cross-embodiment policy was, on average, 50% better than whatever method that laboratory was using for their own tasks. And I would emphasize that each laboratory had a different method that they were using for their tasks. It was whatever was the best method that they had developed in their setting. And this cross-embodiment model, this one is called RT1X, actually outperformed it on average by 50% in terms of success rate. We also trained a large-scale vision language model that was fine-tuned on the RTX dataset and tested it at Google in comparison to the best vision language model that was trained on Google-only data on fairly nuanced semantic tasks that required repositioning objects based on textual command and spatial relationships. And we found that on our hardest generalization evaluation, the model trained on cross-embodiment data improved by over 3 times in terms of success rate over the model trained on only the Google data. And this is very interesting because the Google portion of the data set was actually the largest portion. It was over 130,000 trials out of 1 million. So even the robot that had the most data available to it improved by 3x on the hardest generalization tasks by leveraging data from other robots. And here are more examples of these kinds of semantic tasks that required this high degree of generalization. So this is pretty interesting to me because it suggests that including data across many different robots can actually make models in each domain better than specialized models trained in only that domain. And that's really, I think, bringing us very close to that dream of a robotic foundation model. So to summarize, I discussed some steps we could take towards a robotic foundation model where we can have data from many different robots that we could use to train a general purpose model with some kind of self-supervised objective like goal conditioned learning, um, for example, predicting actions and temporal distances, and then adapt it to a variety of different settings, fine-tune it with RL, or even utilize it for downstream instruction following. And I discussed a few different building blocks, a few different pieces that we can recombine in this way. But of course, in the future, we might want to put all of these together and get one truly general and broadly applicable robotic foundation model. I'd like to thank my students and collaborators, my collaborators at UC Berkeley, as well as my collaborators at Google Research. And I'd like to thank all of you for listening. And I can stop now and take questions. Thank you very much.